So for this meeting, I'm very pleased to present Christian Ohneiser, who's going to be talking to us about pushing environmental magnetic records to the limit, Younger Dryas drought and IPO climate modulation during the Antarctic Cold Reversal in New Zealand. And with that, I will leave you to share.
Cool. Yeah, so the title's a bit of a mouthful, and I hope that I can get through this in 25 minutes. It's going to be a bit of a stretch. This is a paper that you can see we submitted back in 23, but actually the story began in 2017, actually even earlier than that when the core was recovered. Yeah, and it was a slow iterative process of digging away at a magnetic mineral problem to come up with this, with this story here that we managed to finally publish. A quick talk outline. So what I'd like to go into is why is it that we want to reconstruct the Holocene or the Pleistocene? A bit of background knowledge on the Holocene climate down there and in the world maybe. Something about geography of New Zealand and where we are. A little bit about the Lake Hayes core, since that's where it all began, and then what we learned. A note there, this talk is light on paleomag details. I just thought I'd focus more on the story. This is the first time I've worked on lake sediments, and it's also the first time I've delved into the Holocene, or published in the Holocene anyway, so it's all pretty new for me. Oh, next slide. Yes, there we go. I'll touch on this a little bit. Why should we bother with these kinds of reconstructions, and what useful things can we learn? And I'm recycling a slide here from the last talk that I gave for magnets. This is from the IPCC report, and this is a kind of a what happens when the world warms up scenario, right? So we're not in 2020 anymore, and what you can see here is when someone is born, what are they going to feel as they age in terms of a world, a heated up or a hot world or a stormy world or whatever. And it's actually the generation that's born now that's going to maybe see the most interesting parts of global warming. My generation, I'm a 1980s, 81 kind of baby. It's just going to start getting interesting, and those that came before me, they're going to be going out before things really start changing. Well, that's the idea anyway. And there's the different colors are different emission scenarios. So this is a kind of a business as usual end up here, and this is a very low emission scenario if we really start changing how much we're emitting. The IPCC also developed this really, really cool little thing. It's an interactive atlas, and there you can see basically projections for lots of different parameters, how hot, how rainy, how windy, for different sectors of the world. And you can see here, this is that sector there, and it's the rainfall prediction going forward for that sector there, for that whole entire area summarized. So that's a pretty broad view, and you can see it probably stays the same, but it just gets a bit more noisy. So this is all based on model projections. So different countries have their own projections then. This is the second Austrian assessment report. AAR2 came out a month or two ago. And you can see now this is heat projected for the next 100 years or so based on emission scenarios. And you can see things get really granular in here. You can see that valleys get hotter. And so that's more the local view, right? And so most countries will have their own tools as well that they've developed. And it's also roughly aligned with the IPCC emission scenarios. New Zealand has the same. And so this is the little climate models are the input, right? And the climate models predict that New Zealand will get more rain in the south and it'll get drier in the north as things warm up. It's not projected to get too much hotter, and it's not projected to get too much stormier. The ocean is a really, really good heat sink, and New Zealand is surrounded by ocean. So, yeah. And you can see these are all different kind of models that have been used to come up with the scenario. So these are all different types of climate simulations, and the blue stuff or the greenish blue stuff is more rain, and the not blue stuff, the brownish stuff is less rain. And it all shows that the South Island, basically every single one of these shows that the South Island, so this lower island down here, should get wetter. And the North Island here should get drier. So that's models. Last Wednesday, it got a bit windy in New Zealand, and it didn't really make it to international news, but this is from Dunedin here. Let's see if this actually works. Excuse the language, if you can hear it. Yeah, so that's Dunedin. That's not Jamaica yesterday. And that's not a hurricane or anything like that. That's just weather. And so the question is that normal going forward? Is that the way things are going to be? So these trees are about 100 years old, maybe more, and they've clearly tipped over. So they might not have seen this kind of weather before. So what's the normal really at the end of the day? And what's going to change as we go forward? Um, oh, there we go. So I'll jump a little bit forward now into what this paleoclimate situation looks like. And this is another IPCC figure here. This is 60 million years ago, going to a million years ago, and this is a million years ago to 20,000 years ago, and that's 20,000 to today. And this is global temperature. You can see that's gradually cooled down. There's some steps and little wiggles here, and then during the Holocene here, things warmed up a little bit, more than pre-industrial. And then later on, now they're warming up again. And so the Holocene might actually be an interesting, most recent period to have a look at to see what the weather was actually like 6,000 years ago, 12,000 years ago, whatever. Here's that figure blown up a little bit there, and this is now 10 to 2,000 years ago, 1,000 years ago-ish, and this is kind of the Holocene climatic optimum. It's technically a global average, but I don't agree with global averages because they're different depending on where you go. And there's this warmish bit here, then a cooling down, and now the most recent warming up bit here where we are here now, something like that. That's the warm bit that we can get to quite easily with lake cores, and we can learn a bit about what the weather was doing. And I really do mean the weather in those times. New Zealand was a little bit different. And I apologize, these are the two figures that I found, and the ages go in different directions. So this is younger, and that's younger there. And this is the warm period in New Zealand about 12,000 years ago, and theirs is there. So these are different kind of climate reconstructions. And so we had quite a bit warmer climate in New Zealand during the Younger Dryas, which is here. The Younger Dryas is warm in the south and cold in the north. And the period earlier than that, in New Zealand, we call it, or in the south, we call it the Antarctic Cold Reversal, the ACR. And here it was the boiling warm period. And so there's this seesaw thing that might have been going on in the global climate. But anyway, so New Zealand, we probably want to go back to 12,000 years or something like that into a world that was maybe a degree warmer or 1.5 or 2 degrees warmer to see what was going on there. So that's paleoclimate and in the past. A little bit of geography before we get into it. So this is a thing that I stole off Windy. There's Antarctica, colors are temperature. This is the wind. That arrow there shows you where Lake Hayes is. There's Australia, things are warm, and so we're right at this boundary between the cold and the really warm. Now, the South Island of New Zealand, that's in the path of these westerly weather systems. And so it's an oceanic climate. But in the South Island, there's a really, really big rain shadow at Central Otago. So it's a very dry region. But in the South Island there, the wind strength, or in New Zealand, is linked to rainfall. We know that from meteorology, and we also know that from past climate reconstructions. So we think that if we change the wind, we might change the rainfall. But the climate models, as I said before, they all predict more rain going forward. For those of you that haven't been to New Zealand, next slide, there we go, which might be a few. This is the rain shadow here. This is behind the rain shadow. So on this side of the island here, and the Southern Alps are in the way here. And so that red band there is the rain, 12 meters of rain per year in some of these places. And this is in front of the rain shadow. So we go from a rainforest to a desert, basically. Yeah, and so it's a pretty interesting region geographically, and we can learn something about how much of that rain actually spills over into the rain shadow by looking at the lakes. More geography. So this is New Zealand, the North Island here, South Island there, and that circle is where we're going to. And that circle is here. This is Lake Wakatipu. It's a glacially carved lake, and so is Lake Hayes. This is 90 odd kilometers long, very deep. And that box there is Lake Hayes. And Lake Hayes, so these lake sediments, they carry the story of the basin closure. When did the lake form? And they carry the story of these hydraulic changes, so the rainfall or desiccation events, deglaciation, and floods and droughts. All of these things are recorded by the lakes. That's what it looks like from the top of one of the nearby mountains. And it's just there in the foreground. That's Lake Hayes. That's a river that comes from the mountains, from the surrounding hills. It doesn't flow into Lake Hayes, it actually bypasses it. And that's the west, where the rain technically comes from. Not technically, actually, it does come from there for the most part. So lakes are good recorders of climate, right? So this is a picture of Lake Hayes here. And so we've got a cloud here with rain and then a sun with, well, sunshine. And the lake might change. It might start circulating. It might get turned over by more wind. Or if there's a drought period, it might start changing its evaporation regime. So changes in precipitation, wind, desiccation, they all leave these fingerprints on the lake sediment. And the other nice thing is the lake sedimentation rates usually are quite high. So we can dissolve decadal, or maybe even annual changes. At least you can resolve centennial changes. All right, so we're 10 minutes in, halfway there with the time, more or less. But that's just setting the scene. So back in 2015, 2016, this 5 and a bit meter long sediment core was recovered from Lake Hayes. And Jess Senyoza from Otago University, she was a PhD student at the time. She published this paper in paleoceanography, paleoclimatology on the hydraulic changes in New Zealand during the last deglaciation, where she presented the work that she did on this core here. And so this is a core image. It shows you some olive brownish colored sediment here, diatomaceous olive brown, transitions down into this gray silt here. So the record spans last 15 or so thousand years. And we have a radiocarbon age model, a really good one that tells us that's what the how old the sediment core is at the base, and we've got a few dates in the middle there as well. We also have very fine scale laminations as well here, so we can see things on the millimeter scale as well as 20 to 30 millimeter scale. And those variations were the key to the story, really. And you can see some of those here. So this is from the deeper parts here. Normally we see these things, oh, they're barbs, and then we move on. But for us, that's really where the story was. And it's an interesting story because we saw from the data sets that Jess published, she already published, I think she published maybe the susceptibility record. So the magnetic susceptibility record from the top down to about the Younger Dryas. So that's the Younger Dryas in here. And the Antarctic Cold Reversal, it didn't really do a heck of a lot. And then suddenly we see these spikes appearing in the magnetic susceptibility record. And I thought those were quite interesting. We also have a core scanning XRF record here. This is iron normalized by titanium, and so that can be used as a redox indicator, so reduction or oxidation, because the iron is preferentially reduced out and the titanium stays put. There you go, and so you can see there's changes in the redox conditions or the redox in the sediment. And then the other thing is this manganese iron XRF ratio, which is something to do with water column oxygenation that I understand less well. The sediments are laminated, as I mentioned, and during the Younger Dryas, actually, they're organic poor, and there's carbonate in here, which already tells us that the lake started to desiccate at times. So if you get carbonate formation inside a lake, it can indicate desiccation. You've got to be a bit careful how you interpret that, but in this case here, the balance was in favor of desiccation. Sorry, these are the boxes that should have come up before. So yeah, we have these intervals here, which are very interesting. And so I decided to put a class onto this core, a teaching class. So this is a GL 471. It's advanced geophysics course. It's a kind of a pre-master's course. And the aim actually was to generate a paleosecular variation and a relative paleo intensity record, because we don't have many of those from New Zealand. The geocentric axial dipolar inclination should be around about minus 63 degrees at that latitude. And so we thought, oh, this is we've got a radiocarbon age model, so why not have a go at developing one of these? And so the students really got stuck in here. We collected U-channel samples, measured them on a superconducting magnetometer. And it all looked very good. So this is the first half a meter, and we were pretty happy with that. And then slowly as we go down, we noticed that things kind of went a bit pear-shaped there, and suddenly we started missing the origin at about 3 and a bit meters, and then at about 5.5 meters, things started to go really pear-shaped here. So we parked that story there. It was a complex demagnetization behavior, and there's not a chance of making a believable PSV record in the lower section. Maybe the top though. There you go. Yeah. So I haven't haven't forgotten about the top yet. But anyway, this complicated demagnetization behavior led us in 2018 to go back with the students and sample, but this time focus on the environmental magnetic story. And so we collected lots of close-based samples for environmental magnetic measurements. And we found, or the students found, a magnetite and greigite at the base of the core. And they developed some hypotheses for what could cause this change in mineralogy throughout. They presented their findings in posters, and two of the students actually went on to do PhDs, and so they're co-authors on this paper because, yeah, they contributed quite a lot. The remaining students, we actually couldn't track them down anymore. They just disappeared into the world, and so it would have been nice to have a few more co-authors on the paper. So what did we do? Well, we measured hysteresis, IRM forks, and then some thermomagnetic analyses as well. A mixture of low resolution and then targeted high resolution centimeter scale samples, and then even going back to do even higher resolution sampling. So really getting down to the centimeter to centimeter to centimeter sampling, because we realized that's where the story was. We also collected samples from around the lake, so sediment piles that are around the lake, soil, regolith, and basement rocks, just to make sure that we understood what the source was before making grand interpretations about what's making its way into the sink. So in this core, we identified, or then divided it into 3 magnetic mineral zones. There's this top bit here, which is the detrital magnetite and soft biogenic magnetite zone. This middle bit here, the Younger Dryas, which we only found greigite in that zone there. And then the bottom bit here, which is these alternations of biogenic magnetite, biogenic greigite, and greigite. It's very, very interesting. And so so we've got the sediment core here on the side. We've got magnetic susceptibility here. And so this is the susceptibility record, which looks rather uninteresting. We've got these spikes coming down here in susceptibility, so something's going on there. We have the saturation of remnants here, which shows us this broad hump here. We didn't really delve into too much what was going on there because it didn't really look very interesting. The reduce or the reduction of the MRS here, and then we've got this interval in here, which is kind of all over the show for the saturation remnants. And then we've got the coercivity remnants, which kind of doesn't do much until you get in here. Then we've got higher coercivity, and then we have these alternations in coercivity here. I'm going to show you these intervals in more detail now, and a lot of the story actually hangs off the fork diagrams, first order reversals curve diagrams, and the interpretations that we drew from those. So as I said, the susceptibility record is not very interesting, and we have maybe something more interesting in the remnant saturation or coercivity of remnants further down the core, but again, we didn't find that the big story was there. But we did find it's a mixture of detrital magnetite, so the stuff that comes from the schist, from the surrounding rocks, gets washed into the lake. That are these top forks here. So this is one of these forks here. That is the horizontal profile through the fork, so along that line there. And then this is the vertical profile through the fork, and I think that profile is, well, wherever I chose it, probably about there, something like that. Shows you that it's reasonably wide at the base, not very thin, and so that tells us that it's probably a detrital signal in here, and maybe something else going on here. The biogenic one is that characteristic thin line that you see in these fork diagrams here, and this has maybe got a bit more detrital going on because it's a bit more broad at the base down here. It's got a characteristic, very thin vertical profile here. That's a good fingerprint for biogenic particles. And we call them soft because the peak in coercivity is around about between this 20 and 40 milliteslas here when you're going through, I think it's this one here that I'm looking at here, about there. So this is a biogenic soft. So these biogenic particles, they're made by bacteria. The bacteria, I learned a lot when I was writing this. They use them to navigate. I'm not sure where they're navigating to. And some people say, well, they swim using these particles, or they use them to swim. But anyway, they're perfect little magnetite particles in this case here. And they're made by these biogenic bacteria. Magnetofossils they're called, and they're magnetogenic yeah, bacteria, I think that's what we call them. Now the middle bit here, well, I'll call the middle bit with the Younger Dryas here. In this interval here, we've got this high coercivity, low MRS, and very low susceptibility. And in the highish coercivity at 55 milliteslas, and the forks are noisy, but they look like greigite. I don't have much trouble with interpreting this as greigite. I've seen this before. Some reviewers push back saying, are you sure? So we just sent them this. This is different examples of greigite from the literature, and it just all looks the same as what we've found anyway. So the Younger Dryas looks like it's a greigite-dominated interval, and greigite is a reduction, a diagenetic reduction mineral. I'll talk about what the meaning of that is in a bit. Going further down now in the race to the bottom, this is the most interesting interval in here. And we found these high frequency susceptibility alternations going backwards and forwards here, and these alternations of low to high coercivity. The forks told us that it was biogenic hard. So you can see that's now centered more on this 40 to 60 millitesla interval minerals. And then the high coercivity intervals are all greigite. And so this is an alternation of greigite and biogenic magnetite, and greigite and biogenic magnetite. And the beautiful thing is the susceptibility record carries the frequency of these alternations, because the susceptibility told us, without having to measure hundreds of forks, we measured a few, I can't remember how many, and we said this is the association between low susceptibility and low MRS, and high coercivity and high MRS. So I can't remember which round it went. That there was a biogenic magnetite to greigite alternation. So anyway, pack it up and send it to review. And the first reviewer was Ramon Egli, and he pointed out something that we actually missed in our own forks. We didn't see it. That little finger there coming out of the end of this greigite fork here, he said, I wonder if there's a biogenic contribution to this greigite fork. So he suggested we measure more forks very carefully and stack the data. Problem is, I was on the other side of the world already. I was in Vienna and away from the samples and away from the instrument. And so Ramon offered to do that. So we got the samples sent here. And using his very, very clever technique, he generated these beautiful forks using his VSM, a geosphere, where he stacks something like 16 forks and uses the variable fork smoothing function. And two samples here that are the examples here. We've got this thing here, which clearly shows a biogenic thin line here, but also a nice broad greigite contribution. And another sample here shows more of a greigite contribution, but still a biogenic contribution here. Then he did another thing, which didn't make it to the paper because it was too confusing for reviewers. He subtracted one from the other to just leave the greigite fingerprint, basically, here of a greigite mineral. Yeah, so that was a really amazing contribution. And so we turned Ramon from a reviewer into a co-author, because his contribution kind of went a bit beyond what I would expect from a reviewer. So we've got these intervals now, so let's turn all of that into a story, because we want to push environmental magnetic records to their limit. What can we really get out of them? We're going to go from the bottom up now, from the oldest to the youngest. So here's our lake. There's some rainy clouds and some sunshine, and maybe a lake that's turning over, depending on what's going on. Here are some, oh, what's going on here? There's noise. Maybe it's just for me. These are these cubes that I stole from the website Mindat. There is no actual mineral cube for greigite on Mindat, and I think it's probably because no one's actually seen it before. And so in rocks, we have magnetite. It can get eroded, and it can also get made biogenically. But if we take the magnetite and we put it in some sulfide reducing conditions, we can turn it into greigite. And the big difference is that we've replaced the oxygens with these sulfur atoms here. And so that forms under inducing conditions. So for that to happen, we need organic matter and we need iron, right? So the iron comes from the magnetite, and we need to have organic matter there, and then these reducing conditions. And so our hypothesis was that we can erode magnetite from the rocks. We can transform the magnetite to greigite biogenically, because there is such a thing as biogenic greigite. And then maybe we can transform that, or the magnetite from the rocks directly into this chemogenic greigite. Or we can take the magnetite from the rocks, then the bacteria eat the iron out of that and resynthesize the iron to make biogenic magnetite. And maybe you can go backwards and forwards depending on if there's a change in reducing conditions, if it goes from oxic to anoxic, not oxidizing, because that's something else. And then maybe we can transform this biogenic magnetite, if it's biogenic magnetite, via chemical pathways into this chemogenic greigite. So that stopped spinning now. How do I go to the next slide with everything spinning? There we go. Okay, cool. So going from the bottom now, we have these Antarctic Cold Reversal. We have what appears to be redox cycles, and they're picked out by the magnetic minerals. One thing we had to assume was that the reducing conditions were in the lake and on the lake floor, so that they were syn-depositional and that it didn't happen after deposition. And the reason why we've assumed that is because we have magnetite and greigite in alternating thin intervals. So these are happening in between 4 and 5 centimeters, maybe down to 3 centimeters. You go from greigite, which is a reduction product, to magnetite, which isn't. And to have all those coexisting, they need to be isolated from one another. If it would have happened in the sediment column, then our expectation is that the whole entire sediment column would have been reduced and the magnetite wouldn't be there anymore, right? It would have been consumed in the reaction. So we're saying that these alternations are a signal from the lake or from within the lake. So we've got magnetite, oxygenated conditions, not not oxidizing, because that's something else. Greigite is reducing conditions, and so we have these alternations going backwards and forwards. And we said this is likely linked to the wind strength, right? We can have a lake that's turning over, gets more windy, and maybe giving us a bit more rainfall to create these this redox cycle here. So the climate mechanism for that redox cycle, if the climate's windy and wet, this is my lake cartoon now. This is wind, this is rain, and the lake is being stirred. And here are the little biogenic suckers down here making magnetite. So we have strong circulation when it's windy and oxygenated water column, and we have magnetite. If it's hot and dry, maybe it doesn't have to be hot, maybe it just needs to be dry. We have a no or weak circulation, so maybe thermal stratification of the water column, and then an anoxic water column, or at least at the base, and we have formation of greigite. Now that can be biologically or chemically, because we couldn't really tell the difference between the two. These redox cycles are not a new idea. So Ramon published back in 2004 paper, and probably others have done this before, where they've demonstrated these things via paleomagnetic analyses. This is an example from Switzerland, which is, I think, why Ramon was chosen to be a reviewer for this paper. So what makes the lake haze a bit special then? Well, the record there, we did some spectral analyses on the susceptibility data, and we found that these are 50 to 70 yearish cycles. They're pretty regular in the Antarctic Cold Reversal. And that correlates with a local, well, not even local, it's the lower Pacific part, really, the Interdecadal Pacific Oscillation, the IPO. So that's the first part of that title. And that's the first time that this weather cycle, these are decadal weather cycles, have been seen in paleoclimate data. I couldn't find any other evidence of that. So that made it a bit special. But wait, there's more. So what happened during the Younger Dryas? Well, we have only greigite, and there's no evidence of anything biological there at all. We don't have any evidence of biogenic greigite there. They were just classic greigite forks. And so we suggested, we're not the first, but this was the paleomagnetic evidence for a mega drought, or a very long period where there was reduced rainfall into the lake. And we have no cycles in that period at all, so no climate cycles whatsoever. And the other thing was there's an XRF data set, which shows that there's more carbonate in these sediments, which means that apparently this lake was then evaporating. It went into a kind of a evaporitic state without being topped up. So that's our mega drought. And because we didn't find any evidence of anything biogenic in there, we thought maybe these guys, it was so anoxic that even the bacteria decided to move out. So the Holocene, well, we didn't really see much there. The Holocene looks like the lake really hasn't changed much from a paleomagnetism point of view. Today, that lake becomes anoxic in summer. The lake floor is actually anoxic. It's not very deep, it's only 30 meters deep, but the wind stress goes down. The nutrient load is quite high ever since the humans arrived. And so, yeah, it stratifies again and becomes anoxic. So I'm assuming that this anoxic production, we didn't find any evidence of it, but greigite's probably forming on the lake floor today. In winter, it gets stirred again. So we know that in winter, when it's more windy and more rainy, the lake actually, yeah, it becomes balanced again. It becomes oxygenated. So summary here, we've got Younger Dryas, so last 12 or so million years when not 12 million, sorry, 12,000 years ago. The climate was a little bit warmer than today, and we had a period of mega drought. During the Antarctic Cold Reversal, we had this very interesting oscillation. The IPO was functioning there for some reason. It was maybe colder than today, but maybe not actually. Maybe it was the same. We still don't have a really good handle on what the climate was like in New Zealand, but now we know that in the south, we had these strong IPO controls on precipitation in the region. Who cares? Why is this interesting? So this is the bit about pushing these records kind of to the limit without overselling them, I guess. So the climate models here, they predict more rain for the South Island of New Zealand. And the other thing is climate models don't do multi-decadal climate fluctuations very well, actually. They're really, really poor at predicting multi-decadal climate. Our data show that it's a possibility going forward that there's going to be increased drought instead of increased rainfall, and that climate oscillations might actually switch on or off depending on what the climate's doing, how it warms or how much it warms by. The meteorological trends, because these oscillations are very long, we've only got one in 100 bit years of weather data in New Zealand, same as in Europe actually. So you've only seen these oscillations maybe twice or 3 times or 4 times if you're really, really lucky. So we still don't know how they play out or what impact they have. In Europe and probably elsewhere, climate models do not predict these climate oscillations, so they're not part of it, and part of the forecasting. It's not forecasting, but it's part of the climate modeling. And here we have the Atlantic multi-decadal oscillation index that exists as well, and that has an impact on Europe's weather. So I'm going to swing around now to the Arctic to try and make a point. An interesting one, actually. So the Arctic sea ice was meant to be in serious trouble by now. So some of these models predicted that it was maybe we're going to have very soon an ice-free Arctic, right? It was all meant to be going. But actually, the Arctic sea ice hasn't really decreased much since 2004. And so I think it's only when someone points that out, then you realize, actually, yeah, I haven't heard anything in the news about it for a long time now. And there was a paper that was published a few months ago, actually. Minimal Arctic sea ice loss in the last 20 years. So actually, the Arctic's now in not a terrible shape anymore. And these are the models from the IPCC, and those little lightning bolt arrows show you where the Arctic sea ice was in this September, a few months ago. It's almost at the top range of what's predicted, right? It's almost leaving behind the models that the IPCC was using. And why? The only or the most likely reason for the change in that reduction in Arctic sea ice was the AMO, so that Atlantic multi-decadal oscillation. That's what they're pointing to. So these multi-decadal oscillations have can have a big impact on what's going on in our world, and we can see them in the paleoclimate data sets. Here's a paper from Michael Mann, 2021, who said that basically there's no evidence of multi-decadal oscillations in the climate system, and it's all driven by volcanic forcing. Yeah, I don't agree with that. We can conclude that there's no compelling evidence that these things exist. I think they do exist, and I think that they're a bigger part of the story going forward. So conclusions. These magnetic minerals, I think, by pushing them really hard and really going down to that centimeter level, you can learn some really interesting things about, in this case here, a lake. And so magnetic minerals are very, very good environmental indicators of what's going on. And if we look really, really close, we can really learn a lot more than I think what even I expected. We can go down to that decadal scale. At the moment, I'm working on an annual level on another lake core. And we got to remember that climate models are just that. They're useful, but they're not a crystal ball. And so in many cases, the model resolution is now greater than the empirical data. And that's in the oceans especially true because it's orders of magnitude different now in terms of ocean observations versus model output. Multi-decadal cycles exist, but the climate models actually don't do very well with telling us where they're going. And so, yeah, I think we need to do more of these paleo environmental reconstructions to really figure out how they worked, and more studies are needed here. This is why there's Batmans at the end there to put our capes on and going out there and start really looking at that centimeter or decadal scale. That's the full loop, and I'm sorry that took a bit longer than the 25 minutes prescribed. There we go. Cool.
Thanks, Christian. I think that was a really cool talk. I certainly have some questions. I think everyone can give a virtual round of applause. And yeah, if you have any questions, put your hand up or feel free to put your question in the chat. And I certainly have a couple, but I'll wait a little bit for anyone to get theirs out.
As you can see, this paper started in the mid-2023 and we only managed to get it out this March. So it kind of changed quite a lot, and a lot of the finer details of the story just got chucked out in the process.
So as I don't see anything just yet, I guess I'll get things started with a quick question. So that thing that you mentioned about the Arctic at the end was very interesting.
Yeah.
So is that is what you're, I wasn't quite clear. Is what you're saying with that is that the sea ice loss is being suppressed by a current multi-decadal cycle that we're in, or is it that actually there may not be a longer term trend in loss of sea ice because the models have been influenced by a multi-decadal? So like, which is it? Is it that we were sort of in a cycle before which was promoting it, and now we're not, or now we're in a cycle that is preventing it? If that makes sense.
Yeah. I think that's a bit of an existential question, really. I don't know. And I mean, I just like that when that paper came out, they pointed out that actually not much has happened with the sea ice. And it's still within the model boundaries, but if it doesn't start doing something soon, I'm not hoping for it to start decreasing again. But within another few years, it's going to leave what previously were model projections of sea ice loss because of warming. And so some multi-decadal oscillation, they've pointed their finger at the AMO, the Atlantic multi-decadal oscillation, as being the controller of maybe the Arctic sea ice. There's another one, the North Atlantic Oscillation Index. I don't know how these two work, but they're slightly offset, and they have roughly the same 50 to 70 year time scale. But yeah, because they're such long oscillations, we don't, you see them in meteorological records maybe 3 times. That's it. And so the only way to go further back is to either look at what the sailors were reporting, I guess, and use a reconstruction from word of mouth, or start looking at these lake records over the last few hundred years, few thousand years, to see what the impact of the AMO was, and we just don't know, really. I think in Europe, I've heard some people say that it can control when snowfall begins in the Alps, or maybe snow survival in Austria. But yeah, that's weather, really. It's yeah, I don't know.
Thanks.
You feel free to get the paper from the interweb, and then you can fire me off an email if you would like to have a chat about it.
Yeah, I guess if we have no further questions, we might get some in the catch up afterwards. But if that's the case, you can stop sharing, and I will share. Okay. All right, just want to say very quickly, let's thank Christian again with a round of virtual applause for his excellent talk. And just to kind of do some housekeeping, our next talk will be on the 12th of November by Joe Stoner. We don't currently have a title for that talk, but we will let you know as soon as we have one. And if you missed the start of this or you've missed any of our other presentations, feel free to catch up on the MagNetZ YouTube. We upload every presentation to the YouTube channel. And we now have over 135 for you to view because we've been doing this for a while. So check it out. All right. Thanks, everyone.